Radium is a chemical element with symbol Ra and atomic number 88. It is the sixth element in Group 2 of the periodic table, also known as the alkaline earth metals. Pure radium is almost colorless, but it readily combines with nitrogen on exposure to air, forming a black surface layer of radium nitride. All isotopes of radium are highly radioactive, with the most stable isotope being radium-226, which has a half-life of 1600 years and decays into radon gas. When radium decays, ionizing radiation is a product, which can excite fluorescent chemicals and cause radioluminescence. Radium, in the form of radium chloride, was discovered by Marie Curie and Pierre Curie in 1898. They extracted the radium compound from uraninite and published the discovery at the French Academy of Sciences 5 days later. Radium was isolated in its metallic state by Marie Curie and André-Louis Debian through the electrolysis of radium chloride in 1910. In nature, radium is found in uranium and thorium ores in trace amounts as small as 1/7 of a gram per ton of uraninite. Radium is not necessary for living organisms, and adverse health effects are likely when it is incorporated into biochemical processes because of its radioactivity and chemical reactivity. Currently, other than its use in nuclear medicine, radium has no commercial applications. Formerly, it was used as a radioactive source for radioluminescent devices and also in radioactive quackery for its supposed curative powers. Today, these former applications are no longer in vogue because radium's toxicity has since become known, and less dangerous isotopes are used instead in radioluminescent devices. Characteristics: radium is the heaviest known alkaline earth metal and is the only radioactive member of its group. Its physical and chemical properties most closely resemble its lighter congener barium. Physical: pure radium is a volatile silvery white metal. Its color rapidly vanishes in air, yielding a black layer of radium nitride. Its melting point is either 700 degrees Celsius or 960 degrees Celsius, and its boiling point is 1737 degrees Celsius. Both of these values are slightly lower than those of barium, confirming periodic trends down the group 2 elements. Like barium, radium crystallizes in the body-centered cubic structure at standard temperature and pressure. The radium-radium bond distance is 514.8 picometers. Radium has a density of 5.5 grams per cc, higher than that of barium. Again confirming periodic trends, the radium-barium density ratio is comparable to the radium-barium atomic mass ratio, due to the two elements' similar crystal structures. Chemical radium, like barium, is a highly reactive metal and always exhibits its group oxidation state of +2. It forms the colorless Ra2+ cation in aqueous solution, which is highly basic and does not form complexes readily. Most radium compounds are therefore simple ionic compounds, though participation from the 6s and 6p electrons is expected due to relativistic effects and would enhance the covalent character of radium compounds such as Raf2 and Rat2. Solid radium compounds are white as radium ions provide no specific coloring, but they gradually turn yellow and then dark over time due to self-radiolysis from radium's alpha decay. Insoluble radium compounds coprecipitate with all barium, most strontium, and most lead compounds. Isotopes: radium has 33 known isotopes, with mass numbers from 202 to 234. All of them are radioactive. 4 of these 223 Ra, 224 Ra, 226 Ra, and 228 Ra occur naturally in the decay chains of primordial thorium-232, uranium-235, and uranium-238. These isotopes nevertheless still have half-lives too short to be primordial radionuclides and only exist in nature from these decay chains. Together with the artificial 225 Ra, these are the 5 most stable isotopes of radium. All other known radium isotopes have half-lives under 2 hours, and the majority have half-lives under a minute. At least 12 nuclear isomers have been reported. The most stable of them is radium-205 meters, with a half-life of between 130 and 230 milliseconds, which is still shorter than 34 ground-state radium isotopes. In the early history of the study of radioactivity, the different natural isotopes of radium were given different names. In this scheme, 223 Ra was named actinium X, 224 Ra thorium X, 226 Ra radium, and 228 Ra mesothorium 1. When it was realized that all of these are isotopes of radium, many of these names fell out of use, and radium came to refer to all isotopes, not just 226 Ra. Some of radium-226's decay products received historical names including radium, ranging from radium A to radium G. 226 Ra is the most stable isotope of radium and is the last isotope in the decay chain of uranium-238 with a half-life of over a millennium. Its immediate decay product is the dense radioactive noble gas radon, which is responsible for much of the danger of environmental radium. It is 2.7 million times more radioactive than the same molar amount of natural uranium, due to its proportionally shorter half-life. A sample of radium metal maintains itself at a higher temperature than its surroundings because of the radiation it emits: alpha particles, beta particles, and gamma rays. More specifically, natural radium emits mostly alpha particles, but other steps in its decay chain emit alpha or beta particles, and almost all particle emissions are accompanied by gamma rays. History. Discovery. Radium was discovered by Marie Sklodowska-Curie and her husband Pierre Curie on 21 December 1898, in a uraninite sample. While studying the mineral earlier, the Curies removed uranium from it and found that the remaining material was still radioactive. They separated out an element similar to bismuth from pitchblende in July 1898. That turned out to be polonium. They then separated out a radioactive mixture consisting mostly of two components: compounds of barium, which gave a brilliant green flame color, and unknown radioactive compounds which gave carmine spectral lines that had never been documented before. The Curies found the radioactive compounds to be very similar to the barium compounds, except that they were more insoluble. This made it possible for the Curies to separate out the radioactive compounds and discover a new element in them. The Curies announced their discovery to the French Academy of Sciences on 26 December 1898. The naming of radium dates to about 1899, from the French word radium, formed in modern Latin from radius. This was in recognition of radium's power of emitting energy in the form of rays. Subsequent developments. In 1910, radium was isolated as a pure metal by Marie Curie and André Louis Debian through the electrolysis of a pure radium chloride solution using a mercury cathode, producing a radium-mercury amalgam. This amalgam was then heated in an atmosphere of hydrogen gas to remove the mercury, leaving pure radium metal. The same year, Euler isolated radium by thermal decomposition of its azide, Ra2. Radium metal was first industrially produced in the beginning of the 20th century by Biraco, a subsidiary company of Union Minière du Haut-Katanga in its Solon plant in Belgium. The common historical unit for radioactivity, the Curie, is based on the radioactivity of 226 Ra. Occurrence. All isotopes of radium have half-lives much shorter than the age of the Earth, so that any primordial radium would have decayed long ago. Radium nevertheless still occurs in the environment, as the isotopes 223 Ra, 224 Ra, 226 Ra, and 228 Ra are part of the decay chains of natural thorium and uranium isotopes. Of these four isotopes, the most long-lived is 226 Ra, a decay product of natural uranium. Because of its relative longevity, 226 Ra is the most common isotope of the element. Thus, radium is found in tiny quantities in the uranium or uraninite and various other uranium minerals, and in even tinier quantities in thorium minerals. 1 ton of pitchblende typically yields about 1/7 of a gram of radium. 1 kilogram of the Earth's crust contains about 900 picograms of radium, and 1 liter of seawater contains about 89 femtograms of radium. Extraction. In the first extraction of radium, Curie used the residues after extraction of uranium from pitchblende. The uranium had been extracted by dissolution in sulfuric acid, leaving radium sulfate, which is similar to barium sulfate but even less soluble in the residues. The residues also contained rather substantial amounts of barium sulfate, which thus acted as a carrier for the radium sulfate. The first steps of the radium extraction process involved boiling with sodium hydroxide followed by hydrochloric acid treatment to remove as much as possible of other compounds. The remaining residue was then treated with sodium carbonate to convert the barium sulfate into barium carbonate, carrying the radium, thus making it soluble in hydrochloric acid. After dissolution, the barium and radium are precipitated as sulfates, and this was repeated one or few times for further purification of the mixed sulfate. Some impurities that form insoluble sulfides were removed by treating the chloride solution with hydrogen sulfide followed by filtering. When the mixed sulfates were pure enough, they were once more converted to mixed chloride, and barium and radium were separated by fractional crystallization while monitoring the progress using a spectroscope and the electroscope. A similar process was still used for industrial radium extraction in 1940, but mixed bromides were then used for the fractionation. If the barium content of the uranium ore is not high enough, it is easy to add some to carry the radium. These processes were applied to high-grade uranium ores but may not work well with low-grade ores. Production. Uranium had no large-scale application in the late 19th century, and therefore no large uranium mines existed. In the beginning, the only larger source for uranium ore was the silver mines in Joachimsthal, Austria-Hungary. The uranium ore was only a byproduct of the mining activities. After the isolation of radium by Marie and Pierre Curie from uranium ore from Joachimsthal, several scientists started to isolate radium in small quantities. Later, small companies purchased mine tailings from Joachimsthal mines and started isolating radium. In 1904, the Austrian government nationalized the mines and stopped exporting raw ore. For some time, the radium availability was low. The formation of an Austrian monopoly and the strong urge of other countries to have access to radium led to a worldwide search for uranium ores. The United States took over as leading producer in the early 1910s. The Carnotite sands in Colorado provide some of the element, but richer ores are found in the Congo and the area of the Great Bear Lake and the Great Slave Lake of northwestern Canada. Neither of the deposits is mined for radium, but the uranium content makes mining profitable. The amounts of radium produced were and are always relatively small. For example, in 1918, 13.6 grams of radium were produced in the United States. In 1954, the total worldwide supply of purified radium amounted to about 5 pounds, and it is still in this range today. While the annual production of pure radium compounds is only about 100 grams in total today. The chief radium-producing countries are Belgium, Canada, the Czech Republic, Slovakia, the United Kingdom, and the post-Soviet states. Compounds. Radium oxide has not been characterized, despite oxides being common compounds for the other alkaline earth metals. Radium hydroxide, too, is the most readily soluble among the alkaline earth hydroxides and is a stronger base than its barium congener. Barium hydroxide. It is also more soluble than actinium hydroxide and thorium hydroxide. These three adjacent hydroxides may be separated by precipitating them with ammonia. Radium chloride is a colorless, luminous compound. It becomes yellow after some time due to self-damage by the alpha radiation given off by radium when it decays. Small amounts of barium impurities give the compound a rose color. It is soluble in water, though less so than barium chloride, and its solubility decreases with increasing concentration of hydrochloric acid. Crystallization from aqueous solution gives the dihydrate RaCl22H2O isomorphous with its barium analog. Radium bromide is also a colorless, luminous compound. In water, it is more soluble than radium chloride. Like radium chloride, crystallization from aqueous solution gives the dihydrate RaBr22H2O isomorphous with its barium analog. The ionizing radiation emitted by radium bromide excites nitrogen molecules in the air, making it glow. The alpha particles of radium quickly gain 2 electrons to become neutral helium, which builds up inside and weakens radium bromide crystals. This effect sometimes causes the crystals to break or even explode. Radium nitrate, too, is a white compound that can be made by dissolving radium carbonate in nitric acid. As the concentration of nitric acid increases, the solubility of radium nitrate decreases. An important property for the chemical purification of radium. Radium forms much the same insoluble salts as its lighter congener barium. It forms the insoluble sulfate, chromate, carbonate, iodate 2, tetrafluoroborylate, and nitrate 2. With the exception of the carbonate, all of these are less soluble in water than the corresponding barium salts. Additionally, radium phosphate, oxalate, and sulfite are probably also insoluble, as they co-precipitate with the corresponding insoluble barium salts. The great insolubility of radium sulfate means that it is one of the less biologically dangerous radium compounds.